In this video, we're going to derive a beautiful method for figuring out what magic function we can multiply something like this by in order to convert the left-hand side into something that's really easy to integrate using a reverse product rule. This is relatively advanced, and if it's something that you would rather just know the result and come back to this proof later on, that's totally fine. Knowing this derivation is not required in your exams, but I think it's a beautiful thing to see. So feel free to just skip to the end of this video to see the results, and obviously the next video will work through loads of examples, but I do hope if you're feeling confident that you'll stick with me through this. So what we're looking for is a special function, let's call it f of x, such that when I multiply through by f of x, it is just the result of applying some product rule. So let's call that special function f of x. So if we just multiply through by f of x and get f of x dy by dx plus f of x p of x y, and p of x, by the way, is just any function of x. It could be sine x, it could be x squared minus 3 over x, whatever. And q of x is just another function of x. So what I would like is, I would like this left-hand side to be the result of some product rule differentiation. And if the left-hand side is a result of some product rule differentiation, it's going to need to be that this is my u, this is my u dash, this is my v, and this is my v dash. So let's focus in on this u and this u dash. What I'm saying is that f of x, p of x should be what you get when you differentiate f of x. So the derivative of f of x, f dash of x, should be f of x, p of x. Now here's the genius step. If you divide through by f of x, you get f dash of x over f of x. And do you notice, or do you recognize f dash of x over f of x from anywhere? Where do we see f dash of x over f of x, the derivative of a function over a function? Well, it's in Lun differentiation. This left-hand side is the result of differentiating Lun of f of x. So that left-hand side is the derivative of Lun f of x. So, peeling this all away, we can say that Lun of f of x is the integral of p of x. And therefore f of x, and here's the big result, is e to the integral of p of x. So this is our super duper important result. The magic function that you need to multiply through by in situations like this is e to the integral of p of x. When you have a differential equation in this form, dy by dx on its own, that's really important, plus a function of x times y equals a function of x, the magic function is e to the integral of p of x. Let me show you how that works. Let's take an example like this. The first thing to do is to guarantee or ensure that it's in this form with the dy by dx on its own. So I'm going to divide through by x cubed. Dividing through by x cubed gives me dy by dx plus, then 4x squared divided by x cubed is 4 over x. Then we've still got the y, and then dividing through by x cubed here, it's 5 over x to the 4. Okay, now it's in this form, the p of x bit is the 4 over x here. So my magic function, my integrating factor, that's what it's called, is e to the power of the integral of this function here. So it's the integral of 4 over x. Now the integral of 4 over x is 4 ln x. So e to the 4 ln x. Don't worry about the plus c. You can think about why we don't need that. Essentially, it just will cancel all out everywhere because you're multiplying through by everything. I'll show you in a moment, but maybe you can pause and figure out why we don't bother with the plus c. But don't bother with the plus c. That's e to the power of ln x to the 4, and that's x to the 4. So x to the 4 is my integrating factor. I now sweep through multiplying by x to the 4, and that gives me x to the 4 dy by dx plus 4x cubed y equals 5. Once you've done that, it is guaranteed that the left-hand side is just reverse product rule, or rather it's just the result of doing product rule, and we can say that is the derivative of, and it's always just going to be this term here multiplied by y. Because if you've done everything correct, that's your u, that's your u dash, that's your v dash, and so uv is just that term times y. Now we can solve, and it's x to the 4. And this is the same problem we did in the last video. This is just the formal way of doing it. 5x plus c. So y is 5 over x cubed plus c over x to the 4. Okay, a couple of points. One is you might be thinking, but hold on, why do we need to bother with all of this? Because couldn't we have just multiplied through this by x? Well, sure. If you can spot that x is the magic function that does it for you from this starting point, that's fine. Well, it's sort of not actually. In exams, you should show the full working, but mathematically it's fine. It's just there are situations where the integrating factor or like the magic function is not obvious at all. So this is a technique which is guaranteed to work. Convert it back to this form of dy by dx plus a function of x times y equals anything in terms of x, and this technique will work. I do want to loop back to why did we not bother with a plus c? We didn't bother with a plus c because of the following reason. If I had put a plus c here, let's say I'd had e to the 4 ln x plus c, so that's e to the ln x to the 4 plus c. What is that? That's, well, if I split this up, that's e to the c times x to the 4. So that's just a x to the 4. So your integrating factor there just becomes a times x to the 4. But since you're multiplying through by that, you would have just had a times the stuff here, a times the stuff here, and a times the stuff here, and you just divide through by a. So it would just, if you added it in, it would just cancel out anyway. So there's no need for that plus c in the integrating factor stage. Okay, so this is our integrating factor formula. Super important, really beautiful, really powerful. In the next video, we're just going to practice using it in a whole stack of different contexts. So see you there.